Alright, hey guys, and welcome back to my channel. In celebration of the upcoming Super Bowl, which is actually, well, I'm recording the video on February the 5th. I don't know when I'll upload it, but so Super Bowl is today, and so just for its celebration, I thought why not have like a NFL question. And you know how fun is it? We're combining physics and football. So today, my question is, quarterback of the New Orleans Saints, Drew Brees, Hail Marys to wide receiver Marquise Colston in hopes for a touchdown. Brees launches the football at a velocity of 10.7 meters per second at an angle of 55 degrees from the horizontal. So part A, with 6 seconds to go in the game in the fourth quarter, will Colston receive the pass before the clock runs out? And part B, will Colston receive the pass if he's standing 30 meters away from Brees? Now, I'm sorry, if you don't like the Saints, but Brees is my favorite quarterback in the NFL, so I'm going to use him as an example. So now I don't know if you've been through problems like these. This essentially is a projectile motion problem. Anytime you see a problem where you see, there's a given velocity, there's a given angle, and they're asking you, well, I don't directly ask you here, what the time, the flight of time is of the football, but if you carefully read part A, I say with six seconds to go in the fourth quarter, will Colston receive the pass before the clock runs out? So essentially, from the time where Brees launches the football to the time to the point where Colston catches it, we actually want to find out that time. So the time of flight of the football. So how long does it take for the football to basically get to its end position? So that's what I'm asking. Basically, part A is just asking for the time of flight of that. So if you want to reword that, so it's just asking for delta t here. So and then in part B, it's the question is asking, will Colston receive the pass if he's standing 30 meters away from Brees? But in terms of physics, what this part is actually asking is, what is the range of the football? So how far will it travel in the x directions, right? So basically this one's asking for range. And range, or you can call it, delta dx. So it's range in the x direction. So when you have questions like these, okay, yeah, they're pretty awesome questions. They're like, oh, it's about sport and stuff. But the only, I guess, downside to these questions is that they may not necessarily ask you in actual, really obvious terms, okay, in part A, I didn't actually say, what is the time of flight of the football, but you kind of have to get that from the question. And part B, I don't ask you, okay, what is the range? I just say, will Colston receive the pass if he's standing 30 meters away? So you kind of have to read into the questions. So let's get started with part A. And again, if it's a projectile motion problem, the first thing you ought to do is draw a quick little sketch. So and I really apologize for the sketch. I know in advance it's going to be really ugly. So let's say this is Drew Brees. He's standing here, and I know he's much better looking than I'm drawing him here. So he's standing here. He has two hands, obviously. He launches a football, and that's the football. And sorry again, it's super ugly. He launches the football at at a certain angle, and we also know what the angle is, so we will write that out. So he launches it at this velocity at a certain angle. So this is v1, and he launches it, and it eventually it makes kind of like a parabolic motion, and it falls. So and we're assuming there's someone there to catch it. So and we're assuming that both Brees and Marquise Colston are the same height. So basically the football falls back at the same height where it started from. So we don't need to be concerned with anything with height differences. We're not taking that into account. And so it takes a parabolic motion like this, and it falls back here with and Marquise Colston is hopefully here to catch the football, right? Now the distance it travels in between here, and I'm going to draw it in a straight line. So this distance, and it really should be up here, this distance is the range. So this is what you call, from here to here is your dx. So that is what is called the range. So essentially it's the distance the football covers from the point it's thrown to the point where it stops. It just runs out of gas, I guess you could say, and just falls, right? Or in this case, we're assuming it's caught by Marquise Colston. So this is your diagram right here. And also, another piece of given information, we know that this angle right here is 55. And again, I'm just getting that from here. So he launches it at a velocity of 10.7 meters per second at an angle of 55 degrees. So, I really should write 10.7 here meters per second. Now, notice how I write V1. I don't specify V1x or V1y. This is because I haven't broken down into its components. All the question tells me it's launched at an initial velocity of 10.7 meters per second and an angle of 55 degrees. So I can't just say that it's V1x or V1y, and which is what brings me to the beginning of this question, I guess you could say. So let's work with A. So we can break up the velocity into its x and y components, and super easy. If you watched my 2D vector addition problems, you know how to break these components up. So all you do is you draw your final velocity, which is v1. In this case, it's 10.7. And at this point, I'm not writing the units down because it'll just make my diagram super ugly. And then I have an x component and a y component. So this one would be v1y, and this one would be v1x. And again, this angle right here is 55 degrees. I really should be writing the angle inside the triangle, but I guess my diagram's a little bit too small for that. So, you kind of broke it down into your components. And just by looking at this, if you remember your vector addition rules, or how to break it down to components, so I can actually solve for v1y and v1x, right? So let's take v1y. So v1y is it's your opposite, so you have your hypotenuse, you have your adjacent, and you have your opposite. So you have your opposite, you have an angle, and you have your hypotenuse. So this relationship would essentially be your sine relationship, because remember SOHCAHTOA. Now I don't know if everyone memorizes like this. I don't, but it's a good rule. So sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tan equals opposite over adjacent. So in this case, we are dealing with the opposite and the hypotenuse, so we're going to use a sine relationship. So essentially, we can say that sine 55 is essentially v1y over v1. Now, okay, so okay, sine 55, it's a constant, we know what it is. We also know what v1 is, it's 10.7, and we don't know what v1y is. So let's just rearrange for v1y, and that would just be so v1 times sine 55. So there we go, you've got your y component of the velocity, all set up. So similarly, if you can see for v1x, and we'll do it in part B because that's where it's required. We can solve for v1x too, and in this case, we have the adjacent and the hypotenuse and an angle. So I would use the cosine relationship. But anyways, so let's continue on with part A. And just in case you've forgotten, part A is asking, with 6 seconds to go in the fourth quarter, will Colston receive the pass before the clock runs out? So I'm essentially trying to find the flight of time of the football. So how long it takes, for this motion to be completed. And so again, always start off with your given, and we know that. So we definitely know this. That's straight up from the question. We also know that it starts off. We're assuming that it starts off at a vertical displacement, or like the position is 0 meters, because like I said, we're assuming this position where Breeze launches the football from to be 0. That's our reference point. So just in case it's confusing anyone, I'll probably write it down here. So I'm just gonna say assume vertical D is 0. So that's what I'm basically saying here. So that's reference point. So the point where Breeze is launching it from is 0 meters. So you can think of it as, okay, it's where he's launching it from is ground level. Although I know it's not the ground. The ground is at his feet, but we're just taking this point as a reference point. So this is a reference point, and it's 0, just to avoid any complications, because that would make this problem, a little bit more complicated if we're taking the quarterback and the wide receiver's height into consideration, and that would be a little bit complicated for this level. I'm doing it for a senior physics, so like your grade 11 or grade 12. So it would be a little bit too complicated for this. So we're just going to assume that the point where he's launching the football from is at 0 meters. So once we have that, so we can say that, okay, perfect. So he's launching it, so delta dy is 0 at this point. Now it is in motion in the air, so there is obviously going to be a force of gravity, or acceleration due to gravity, I should rather say. So it would be essentially AY would equal negative 9.8 meters per second squared. And notice I write negative. It's because the acceleration due to gravity is always pulling things down, and as a rule of thumb, you generally define any upward motion as positive. So, and I really should have said that in the beginning. So any upward motion is positive, and because acceleration due to gravity is pulling it down, I'm going to say it's negative 9.8. So we have that, and what else do we know? Well, we don't really need to know anything else, because from our awesome key kinematics equations, we can. Oh, my bad. The unknown we're looking for is delta t. So you should really be writing it like that. So what equation can we use? Well, there's a bunch of equations, but we know v1, we know delta dy, we know ay, we just don't know delta t. So the equation we can use is here we go, delta d, and this is in the y direction, so make sure you write down your components. So delta dy equals v1y times delta t plus 1/2 times ay delta t squared. So this is essentially the equation you are going to use. So actually this should be E, not S. This is not the solution we're doing, this is the equation we're using. So this is the equation you should be using for this part, and so I will continue the solution for this problem in part 2 of the video.